So, we'll continue our discussion of virtual memory, which we covered in the previous video. When we refer virtual memory, the keywords which comes to our mind are virtual memory is not actual memory. Virtual memory is opposite to physical memory. Virtual memory is used for converting the logical addresses for converting the logical addresses to physical addresses. The mapping table is a data structure which is used to do this translation from virtual logical addresses to physical addresses. The virtual memory space in few literature is referred as address space, while the physical memory is referred as memory space. We know that pages are the logical pages, while the blocks are physical memory blocks, which are again, uh, for simplicity, page size and the block size is similar. Pages are of logical address, pages are of programs, uh, pages are of virtual address, while the blocks are of main memory, physical memory. And this paging technique is used to swap the pages. Whichever page is required in the main memory is brought there, and whichever is not required, depending on various algorithms, it may be swapped back. So that is page replacement algorithm. Now let us try to go back to our topic through various diagrams which we have taken from either Morris Mono textbook or from Hamachar, which is the prescribed book for us. Let us look at this Morris Mono diagram. If you look at this diagram, what you can see here is it is indicating the relationship between address and memory space. So hope you remember this word address space. So address space we were referring for virtual memory, while the memory space we are referring for the physical memory. And you can see here the left part is the address space, so which indicates the virtual memory, which indicates the virtual logical addresses, and this is implemented with the help of auxiliary memory, and auxiliary memory is secondary memory. And you can say here the address space is denoted by n, and in this example, in this diagram, the address space, virtual logical address space n, the value of that is 1024k, which indicate 2 to the power of 20 address lines. If you look at the memory space which is on the right side, so memory space is the physical memory, and here you can see the memory space size is 32k, and the number of address lines are 2 to the power of 15. So this is how the interrelationship between the address space and memory space occurs. Let us say on the auxiliary memory, the program which you have written, maybe in Python or C or Java, it is available in this auxiliary memory, and this program needs to be executed by the CPU. Then that program from the auxiliary memory is to be brought into the main memory. It always happens that the entire program may not be possible to bring in the main memory, so some part of the active program is brought into the main memory. That's what is the concept of virtual memory concept. uh, if you look at this second diagram, denoted by figure 12.17, you see a data structure called as a memory mapping table, right? So this memory mapping table actually converts these virtual addresses into physical addresses. It actually translates the virtual addresses into the physical addresses. So in some other literature, maybe in Hemachar book, it may be called as something else like paging table. Here in Morris Mono textbook, it is called as a memory table, memory mapping table rather. So you can see here there is a virtual address and there is a virtual address register, and this memory mapping table, with the help of memory table buffer register, will be generating the physical addresses, and the main memory will be using those physical addresses in along with the main memory buffer register. You can see the concept of pages and the blocks here. You can see the concept and pages and the blocks here. You can see by looking at this, the memory space is divided into blocks, while the address space is divided into pages. What is a memory space? The physical memory, main memory. So your main memory, physical memory, in this example, you can see that it is divided into blocks: block 0, block 1, block 2, block 3. So the size of the main memory space is 4K. It means each block size will be 1K. The number of address lines here you can see. This is an example rather, 2 to the power of 12. Similarly, on the left side, you can see the address space. Address space is virtual space, virtual memory space, the program generated addresses. So you can see the size of this is 8K, and this address, virtual address space, is divided into pages. So you can see here 8 pages, page 0 till page 7. So pages and the blocks are of same size. As we said earlier, blocks are sometimes also called as frames. Blocks are also sometimes called as frames. If you look at this diagram, which is from our prescribed syllabus, you see a data structure here called as a MMU. And in the previous diagram, it was also called as a mapping table. Here, this MMU component, the purpose of MMU component is, it is actually memory management unit, and it will be converting the virtual addresses into physical addresses. So what the processor does, the processor has to execute a program. For executing the program, the processor requires that particular data, that particular instruction, uh, whose virtual addresses are there. Now, those virtual addresses are converted into physical addresses, and those physical addresses will be searched in the cache. If they are not in the cache, they will be searched in the main memory, and with the help of, if they are not in the main memory also, then using DMA disk from the disk storage, ultimately the required data will be transferred for to the CPU for execution of the program. So this is actually the virtual memory organization, how it goes. Let us look at the next diagram. So actually we are making walkthrough of all the diagrams which are related to virtual memory from the textbook Morris Mono and the textbook Hamashar. What you are seeing here, you are seeing here a data structure called a page table. Okay, so what you are seeing here, here your virtual addresses generated by the processor. So this virtual addresses generated by the processor, how it is divided, it will having the page numbers, and it will be having the offset, it will be having the offset. So page number, so what the page table based register consists of, it consists of the first address, it consists of the first address of the page table. So from that you can add the offset, and you can look at the page using the page table, you can look at the particular page which you require, and that can be converted into a page frame. So what is a page frame? Previously we mentioned blocks, right? So blocks of main memory, same thing is page frames here, page frames here. Okay, so now if you look at this data structure page table, what it consists of, so it consists of the page frames, and it consists of the control bits. Now, as I said earlier, the page frames are nothing but blocks. As I said earlier, the purpose of virtual memory is also not just translation from virtual address to physical address. The purpose also is bridging the size and speed gap between main memory and the secondary memory. You have a page table data structure, right? Now what this page table data structure consists of, it consists of the locations of every page in the main memory. You have a data structure called as control bits in the page table. What is the purpose of these control bits? It will check the validity of the page, whether the page is valid or invalid. It will check if the page is updated or modified. If it is updated, it needs to be written back to the main memory. It also contains other control bits like read write permissions, restrictions, etc. Now, what you are seeing here is one more data structure called as TLB. Let us look at the long form of TLB. TLB stands for Translation Look Aside Buffer. TLB stands for Translation Look Aside Buffer. What is TLB? Actually, it is a small cache. It is a small piece of cache. It is a small piece of cache. Why this TLB is required? As you cannot keep all this page table and everything in the MMU. in the MMU. The ideal thing is keep everything in the MMU, but it is not possible because MMU is limited as it is processor bound. Hence, page table is kept separately. Page table is kept separately. But to enhance the performance, what can be done is some part of the page table, this data structure is implemented through this TLB. You can look at the TLB here. You have the virtual page number, control bits, page frame in the main memory. Same contents are there. Same contents are available. Okay. Now coming to page fault, the word page fault. What is the meaning of a page fault? For that, we need to remember page. What is a page? You have your logical memory divided into pages. So what are pages? Pages, you can say, it is analogous to, let us say you write a program of 100 pages, 100 lines. These 100 lines, let us say you divide it into 10 pages. So you can say there are 10 pages of this program. So for executing a program, the program is to be brought into the main memory. The program cannot be brought into the main memory completely. So part of the active program is brought. So whenever a CPU does not see the page is required for execution of the program, then it raises a page fault. Then the MMU, memory management unit, will intimate the OS. The OS will generate an interrupt and it will be carrying out the page replacement. What is the page replacement? It will be bringing the required page and it will be taking out the page not required. How it will decide which page to replace? Using the FIFO or LRU mechanism. What is FIFO? We know that FIFO stands for first in, first out, and LRU stands for least recently used. This is what we wanted to discuss today.